Hello guys, today I'm gonna describe to you, as I promised before, a little bit the algorithm and implementation of the PBE workflow that I described in the other video. So in the other video we mostly devoted our time to the demo script here, where basically the more practical aspects were covered. But today we are going to look at the two functions that basically make up the core of our PBE simulation. So we have this PBE function and EQBRM solver, which are basically the two backbones of the structure of our workflow. So let's start with EQBRM solver, which is basically a function providing an interface with PHREEQC. And this is done via PHREEQC COM objects. So for this reason, you have this limitation of working only in Windows, but there are also workarounds to work, for example, with Linux. I'm not going to go over the details of that, but just to put it out there, it is a possibility. In the same fashion I usually do with my scripts and functions, everything is with comments, and functions obviously start with a description of what are the inputs and what are the outputs. Obviously, you may not be interested in all of the outputs. You can just replace them with this little sign as I write here, and just skip out that specific output to save some space when you are saving your variable. So basically, this interfacing function has been written in response to the needs we have for the specific problem of precipitation. Usually we are dealing with mass balances in this particular case, and for that reason, the input to the function is typically the experimental conditions, let's say temperatures, and the parameters for defining the thermodynamics of the system, like the equations, the elements that you have, aqueous species, gaseous species, so on and so forth. And maybe the most importantly, one of the inputs is the elemental concentrations, which you put into the system. Imagine that you have a pot, you put in different elements into this pot, and then you do this speciation calculations, either assuming no solid is forming or by enforcing a solid liquid equilibrium by setting this flag into 1, and you get different outputs in terms of how much solvent you have, what is the solution density, elemental concentrations, concentrations of different species, their activities, saturation indices, pH values, ionic strengths, and finally this output PHREEQC headers, which is basically the headers generated for the output of communication with PHREEQC. So it has like different headers describing, for example, now we have the concentration of each species, now or in with what column we have the activities of different species, so on and so forth. So the input and output is very straightforward. I will quickly go over the inputs. So you have to put in the PHREEQC COM object, which you can basically activate using the syntax, this command. If you do not provide it automatically, the function will activate this COM object. But of course, if you not provide it, then every time you're calling the function, it has to be loaded. It may add some computational burden to your system. So it's better if you have a large number of computations to provide it externally. Then we have the list of elements, aqueous species, gaseous species, which should be consistent, as I mentioned also in the other video, with the database, thermodynamic database that you have here for cementitious systems. A very good database is SemData18, but you can also use any other database like the one from Lawrence Livermore National Lab, or the default database of PHREEQC, which is also a reliable thermodynamic database. Then we have this flag matrix, where the first row denotes the elements, the amount of which has to be calculated by enforcing a gas liquid equilibrium. And the gaseous species that has to be used for this purpose, the index of that gas is written in the second row of the column, in the second row of the matrix, sorry. So we have a 2-row matrix. In the first row, we have the index of the element that has to be enforced by gas-liquid equilibrium. And in the second row, underneath that specific element, we have the index of the gaseous species that we use for enforcing this gas-liquid or vapor-liquid equilibrium. And we have solid species list. We have the index of the solid phase that is not already in the database. You can define different solids. Of course, again, if you are dealing with kinetics, because of the current limitation of the code, it has to be defined in the first spot, spot of this list. Then we have this SLA flag. If you're interested in solid liquid equilibrium calculations, you can set it to 1. It will return 2 sets of outputs. One set is for local equilibrium, assuming no solid is forming, and the second row is for solid liquid flag, pretty much similar to what you would get also in PHREEQC. So when you are defining a solid liquid equilibrium in PHREEQC, first it calculates the equilibrium for the aqueous solution, then it will also enforce the solid liquid equilibrium and reports both sets of data. Then we have the dissolution reaction and the properties of the solid or its dissolution, as you see here. Then we have the experimental temperature in degrees Celsius, the amount of water that you have in your pot, elemental concentrations that you have in the pot, and the saturation index for the gaseous species, which in PHREEQC is defined by definition log 10 of the partial pressure of that gaseous species. Then we have set pH, which is basically a numerical value to which you want to fix your pH. For example, if you have constant pH experiments, if not, you can just leave it empty and then the pH will be calculated. Then we have, if you have a pH fixing, then you have to also introduce a compound, and the element in that compound, that the amount of which has to be calculated by pH fixing. So for example, if you want to fix the pH with sodium hydroxide, you have to here provide NaOH as the input for fixed pH compound, and then the corresponding element is sodium. The value of this will be adjusted by charge balance to attain fixed pH. Then we have, let's go down and take a quick look also at outputs. We have the mass of water after it iterates to have the solution density converged. Then we have element concentrations, species concentrations, activity, saturation indices, pH, ionic strengths, and the headers of the output from PHREEQC. So I will also quickly go over the commands that we have in the program. So we start with initializing the output of PHREEQC, the headers for the outputs of PHREEQC. So then we have to load the iPHREEQC com object if it is not already provided to the program or function, better to say. Then we have to start accumulating lines. So basically this iPHREEQC has this command, clear accumulated lines, which clears up all the lines written so far, if any. This is important to make sure that the calculations are not interfered by previous calculations. Then here we have a setting for knobs, which essentially controls the step size PHREEQC takes at each iteration, and by reducing that from the default value of 100 to 3, we managed to avoid convergence problems that you sometimes encounter with PHREEQC. Then we define the phases. If we have fixed pH, we have to define a fixed pH phase. Then we have to also define solid phases, if any. Then we have to define the initial solution. So you provide a temperature units. Obviously, you're here working mainly with SI units, unless otherwise mentioned. We have density, and then we have the amount of water. Then we have to, for different elements, either put in the amount of that element or calculated based on enforcing the saturation index with respect to that gas, or more precisely by enforcing a partial pressure. Then if pH is set, if pH is not set, you calculate pH based on charge balance. If it is set, you fix it to the fixed pH value, and then you calculate the elemental balance for the element that is in the compound you use for fixing pH based on charge balancing. In the normal sense, you usually calculate pH based on charge balance. Then if we have solid liquid flag, we also have to do calculations, again considering fixed pH situation, enforcing a partial pressure of gases, and of course trying to enforce solid liquid equilibrium with respect to different species. So you provide zero amount and keep dissolving until you reach solid liquid equilibrium. Then here in this section we catch the outputs using again we accumulate lines and try to catch the outputs. So we with this keyword selected outputs, we don't need, for example, simulation information states, but for example some information we do need. For example, pH is important. PE here we're not interested. If for some reason you're interested, you can play with this and adjust it to your needs. And yes, that's pretty much it. Then at the end we have to run this accumulated lines, and if the command PHREEQC.run accumulated is equal to 0, then everything's happy, we get the output, and we will distribute it among different function outputs. Okay, now that we know this interface to PHREEQC, let's also take a quick look at PBE. So basically, if you have some problems with any part of the algorithm, I strongly suggest you to take a look at these two papers from our group, specifically for the algorithms implemented in the current versions. In the current version, you should take a look at this article on uncertainty sensitivity analysis of mechanistic kinetic models. But if you want to know more about the experimental system or some of the basic equations for different calculations, you can also take a look at this older paper from our group. So here we have this core PBE function. So the task it does is basically integrating the set of ordinary differential equations that we have, which is comprised by the PBE equations, mass balances, plus the equation for number of particles, number concentration of the particles in system. So again, we have different outputs. We have the time steps over which we want to have the output of integration, let's say. We have the PHREEQC object, we have elements, aqueous species. These are the same as before. Then here again, I have to emphasize only one solid can precipitate, and it has to be the first solid in the list of solids in solid species list. Then we have this stoichiometry of the solid that is precipitating, ordered similar to elements, and we have this new precipitating solid, which is basically the sum of stoichiometries of different aqueous species except for water, when we have the solution of the solid. For example, if calcium carbonate is dissolved, we produce one calcium, one carbonate, so this new parameter will be 2. We have the temperature, element reactant concentrations. So this is basically the reactant concentrations inside the reaction at time 0. Then the experimental setup is semi-batch. It could also be batch, of course, but in the more general case of semi-batch reaction vessel, we have also inflow concentrations. Then we have the partial pressures of gases. We have the volume, initial volume in the reactor. We have the added volume, the flow rate of addition, set pH, fixing pH compound, fixing pH element. We have the kinetic parameters, so we have interfacial tension, relative cohesion energy, kinetic order of growth, linear growth rate coefficient, and kinetic order of growth, and finally H2 thickness aspect ratio, because in this particular system we are assuming we have cuboid shaped crystallites. Then we have 4 outputs based on which we can calculate any other output that we are interested in. So we have number concentration of particles as a function of time, quadrature points, which includes quadrature weights and non-weighted abscissas in SI units. We have the moments of crystallite size distribution, again in SI units, and we have elemental concentrations as a function of time. Then quickly, let's take a look at how everything works. So first we calculate this diffusion coefficient based on Stokes-Einstein equation, and knowing the building unit sizes and the viscosity of the water, which is temperature dependent. Then we will set up the initial conditions and initialize the scheme for the solution of the PV equation. So here we by default use 3 quadrature nodes. We can also increase it or decrease it if you're interested in. We have the shape factors for crystallite surface area and volume. We provide the initial conditions. We have to use a seeding scheme as described in the article. For numerical reasons, we cannot start with 0. So we provide a very small number concentration of particles and crystallites and very small sizes, and start integration by that. This is very small compared to the typical values we have in the precipitation system once nucleation starts. And we have to finally initialize the initial condition for different element concentrations. If you are using volume, if you're providing volumes, let's say, here the assumption is volumes are measured at room temperature. So let's say you are preparing a solution. The volume that you are measuring, if you're not working based on mass of solvent, then the volumes are typically measured at room temperature. You usually don't measure volumes at, let's say, 50 degrees Celsius. That is the underlying assumption for this whole code. But generally, you can also work at other temperatures, of course. Only the volumes you are reporting are, and the concentrations, if in terms of moles per liter, are at room temperature. Then we set the absolute and relative tolerances. I strongly recommend to start with these tolerances. Then if you are not satisfied with the accuracy of the higher order moments, based on the methods that you can cross-check as described in the paper, then you can maybe comment this line, uncomment these smaller values. It takes more run simulation time, but it gives you a more accurate result. Then we run the ODE integration function, ODE15S, because we have a stiff set of ODEs. I will go over this in a bit, but once the integration is done, we assign the outputs pretty much straightforwardly. Then we have this nested function, ODE function, which is basically calculating the dy over dt for different dependent variables. And everything here is somehow either scaled or scaled and locked and transformed for robustness results, for robustness reasons. For example, the n particle is not directly followed as a function of time. We are following the log 10 of n particle by t as a function of time. That is why when in the function at the beginning, it has to convert everything by raising y1 10 to the power y1. Or for example, instead of following moles, because the moles are in the range of 1 for this precipitation system, and generally for precipitation systems, we follow everything in terms of millimoles instead of the SI unit, which is mole. Then we have to take care of the fact that flow rate is not always given flow. At some point, the added volume becomes 0. It's a semi-batch reaction. Then we have input of different element concentrations to calculate the local equilibrium. And then from there, we can calculate the supersaturation ratio. And we also somehow unfold or maybe anti-log, calculate the anti-log of these dependent variables to get weights and abscissas. Abscissas, of course, in nanometers, and then from there we can calculate abscissas in meters. So yes, may have to correct this. So this one is nanometers, this one is meters. Okay, then we have this moments, right? So this is nanometer. Okay. But then we calculate the moments, we calculate the matrix in the DQ-MOM algorithm. We have the scale matrix, which is for preconditioning, and the rest of the calculations is pretty much described very well in the article. If you go to section 432, or this is the thesis, basically in the third section, subsection 2, you can find the detailed derivation of all the equations, how these work. Thank you very much for your attention. Please send me an email if you have any questions. I'd be happy to help.